Okay, so for today's lesson, we're going to go a little bit more in depth with tangent lines. You should be on page 104 of your notes. And so we're just going to go through these examples and kind of just see how tangent lines work a little bit more in depth, and then learn about approximating tangent lines, which is really, really important. So a lot of this will be review, a little bit of it will be new. So first question gives us g of x equals 1/2 times the quantity of x plus 2 squared minus 4. And it asks us to first find g prime of -4 and explain what that value represents. Now, a big thing, before you can ever find g prime or f prime at a number, you always need to first find g prime of x. This is really important. So first you want to find g prime of x, and then second, you can plug in the number. Always be careful about that. Do not try to plug in first and then take the derivative. You'll always get 0, which is wrong. So first, always find the derivative. Okay, so before we can find the derivative, actually, we need to rewrite g of x as a polynomial. So what I'm going to do is kind of rewrite g of x. And let's do this as 1/2 times x plus 2 times x plus 2. We're going to need to FOIL this out. Minus 4. That's going to give us 1/2 times, when we FOIL this, if you use the shortcut, x squared plus 4x plus 4 minus 4, right? We square the first, multiply them together, 2x, 2 times x is 2x, multiply that by 2, and square the second. That's going to give us 1/2 x squared plus 2x plus 2 minus 4. When I simplify, combining like terms, I like to underline my x squareds once, my x's twice, and my numbers 3 times. That kind of helps me to simplify and to combine like terms. So 1/2 x squared plus 2x minus 2. So this is what g of x was equal to. So now if we want to find g prime of x, right, g prime of x, we'll take the derivative of that. So g prime of x, squared 1/2 times 2 is just 1. So that's x to the first power. And then plus 2, right? The minus 2 goes away. So our derivative is just x plus 2. Now that we found the derivative at any x, now we can plug in -4, right? And we can plug in really any number to the derivative to x plus 2. So this is -4 plus 2, which is -2. So that's our answer for g prime of -4 is -2. Box that, underline it. Now, it also asked us to explain what does this represent in terms of the function. So what we'd say is that g prime of -4 equals -2 represents the slope of the tangent line at x equals -4. Maybe the tangent line of g of x might even be more specific. So the tangent line of g of x at, I wrote x equals -x, at x equals -4, right? And what is that slope? If you want to be even more specific, the slope of the tangent line at x equals -4, say, which is -2, if you really wanted to get specific. Okay, so it's the slope of the tangent line. Right, we talked about this yesterday. Whenever you're explaining, justifying, you always want to kind of have a what is it? It's the slope of the tangent line. Where is it? It's at -4. And the what is it could have also been like the -2, right? So you could even say the slope of -2, or the slope of the tangent line is -2 at x equals -4. Okay, next one, find the equation of the tangent line at x equals -4. So we're always going to put x1, y1, and m whenever we see the equation of a tangent line. So x1 is -4. To get y1, we plug into the original. So f of -4 in our original, and really, you could do g. You can either do this where we expanded it out, plug it in there, or you can plug it in where it was factored. Either way works. I'm going to do the factored way. So 1/2 times -4 plus 2 squared minus 4, right? 1/2 times x plus 2 squared minus 4. So this gives us 1/2 times negative 2 squared is going to be negative 2 squared is positive 4 minus 4. 1/2 times 4 is 2. 2 minus 4 is negative 2. So we actually end up getting the same y value as our slope, just kind of a coincidence. It's not always going to happen. And so that gives us y plus 2 equals negative 2 times x plus 4. Now, you could, it says to sketch this. You could solve for y and put in y equals mx plus b to sketch it. Or you could just realize, hey, wait, this coordinate is at negative 4 comma negative 2. That's where the coordinate is, at x equals negative 4. And I know that the slope of the line is negative 2. That's our slope. And so, down 2 over 1, down 2 over 1, maybe up to left 1, and, use a ruler and make this line nice and straight, or some kind of a straight edge. Now, I've had students ask in the past, if I have the graph, do I actually have to plug it into the equation? Instead of plugging this in, couldn't we have just looked at this point? And the answer is absolutely. If you're that smart, do it. Right? The coordinate was negative 4, negative 2. If the AP test gave you a graph, you can use it. You could have just put negative 2 here because you saw it on the graph, and you could have skipped all that work. So absolutely. So now I want to use that equation, and I want us to, using the equation, find the value of y when x equals negative 3.9. So our equation was y plus 2 equals negative 2 times x plus 4. So we're going to do y plus 2. We're solving when x is negative 3.9. So this gives us y plus 2 equals negative 2 times, now, negative 3.9 plus 4. You can just kind of think in your head that's the same as 4 minus 3.9. You can always, change the order. 4 minus 3.9 is just 0.1. You guys should be really, really confident multiplying decimals. It's really not a hard concept. You just imagine that it wasn't a decimal and then move it back. So what would have been negative 2 times 1? Negative 2 times 1 would have been negative 2. But now just move the decimal back one spot and it's negative 0.2. That should be very easy for us. So y plus 2 is equal to negative 0.2. I'm going to put an arrow. That's going to give us y equals, now subtract 2. We're going to get negative 2.2. So that's our answer for the y. That was on the tangent line. So on the tangent line, when we plug in negative 3.9, we got negative 2.2. Next, it's going to ask us to find the value of g of negative 3.9. Now that's going to plug into g. So g of negative 3.9, you're going to plug in into g, right? 1/2 times negative 3.9 plus 2 squared minus 4. And I don't really want to do that by hand, so I just hopped on my calculator. If you guys have your calculator, you can try using it. You could also just use Desmos or a phone calculator for right now. And when you type this into your calculator to 3 decimals, I got negative 2.195. So negative 2.195. So what this means is on the graph, right, at negative 3.9, if we really zoom in, where's negative 3.9? It's like right here. On the actual graph, on the black graph, it was negative 2.195. And then on our tangent line, which is this red graph, on the tangent line, it was negative 2.2. What do we notice about those 2 points? They're very, very, very close to each other, right? You even just look at the y values, right? Negative 2.2 and negative 2.195. This would round up to negative 2.2 if you rounded to 1 decimal. In calculus, you're never, ever going to round to 1 decimal, right? So these are different numbers. They're not the same. Do not tell me that they're the same. They're not. But they are very, very close. Okay, so what do you notice about these two results? They are very close. They're not the same, but they're very close. So what do we think that that might mean? That might mean that we can use the equation of the tangent line to approximate, right? Because they're close, so they're not going to be exact, so we're not going to be able to get the exact answer. But we can use the equation of the tangent line to approximate values close to the point. Now, I want to be very careful about this and kind of look at what I mean by to the point. That point I'm talking about is -4 comma -2, because that's where the tangent line is for. If we zoom in here, right, these two lines almost look like they're overlapping right here. So anything that was really close to x equals -4, right, that's what we plugged in, right? We did -3.9. That's really close to -4. It's a good approximation. It's very, very close. But if we look at, if I wanted to approximate at -2, right, we'll wait for this to load. If I wanted to approximate at -2, what's the actual value of g of -2? G of -2 is equal to -4. But on my tangent line, the y value is -6. These are not close. -4 and -6 are not close at all. Okay, and if we wanted to even get more extreme, right, at like +2, we would have gotten 4. And for the tangent line, we would have gotten something way, way smaller, right? That slope is -2, so you can figure it out. -8, -10, -12, -14. So 4 and -14 are way, way, way off. So this only works for these tangent lines is, very close around there. You can see that the red line and our curve kind of overlap. So it's really only for decimals that are very close to that. And what happens is that this approximation, actually using this approximation, as we get even closer and closer and closer, that's actually how your calculator is able to solve for things that might not exist, get approximations for things that might not exist when they're doing limits, right? Like when you get a DNE answer, your calculator just uses a tangent line and it gets really, really, really close. And then, we did 3.9, but if you did like 3.999999999, it would be so close that the numbers are the same. So that's actually how your calculator does it. And that's why it's important to learn these, is if you ever get into any kind of software, any kind of coding, programming that involves math, it's really important to know how to work with those, kind of equations that don't work. And before calculators, this is how mathematicians would do it, right? Like back in the 1800s, 1700s, before mathematicians had calculators, if they wanted to figure out an answer, they would have to use these tangent lines. Okay, so let's move on to this next one. Now, we're still going to talk about tangent lines, but just a little bit differently. So this first question gives us a new equation, g of x equals 2 square root of x minus x plus 2. And again, we have the graph. And we're asked, based on the graph, at what value does the graph have a horizontal tangent? So kind of looking at this, to me, it looks like it's about at x equals 1. Now, if we're going to justify this, goes back to yesterday, okay? What was our justification for horizontal tangent? Horizontal tangent matched up with when the slope was 0, right? And that could have been like at a maximum or a minimum. So, we could say, based on the graph, it looks like, g of x, I'm going to just say like appears because it's on the graph, to have a horizontal tangent at x equals 1. You're never going to get asked this on the AP exam because it's too like kind of opinionated. But just for our homework, we're kind of looking at this. And the reasoning, maybe one of two reasons, either because g prime of x was 0, or maybe you even said because like g of x has like a relative maximum. Maybe that's kind of why you picked it. Something like that. Now, what you might need to do is show the algebraic analysis that it supports it. Prove that it has a horizontal tangent there. So what do we know about horizontal tangents? We always know whenever we see the word horizontal tangent, we always know that the slope there, that f prime of x there, is equal to 0. This was from yesterday, or actually Monday's notes, right? On Monday's notes, we talked about horizontal tangent, right? We had that table of justifications. Horizontal tangent matched up with slope f prime being 0. So in this case, we're using g of x, but basically we know that g prime of x is going to have to be 0. So let's actually take the derivative. So again, in this case, before I can take the derivative, maybe off on the side, let's rewrite this in polynomial form. So 2 square root of x is going to change to x to the half minus x plus 2. So we take that derivative, half times 2 cancels out to 1, x to the negative half minus x. And then if you want to rewrite this to make it easier on yourself, right, this is 1 over x to the half minus x. And if you want to even rewrite that in radical form, that's 1 over square root of x minus x, just because it's going to be easier to plug in there or solve. So what are we going to do? We're going to set this equal to 0. So we're setting our derivative equal to 0. I'm going to just kind of rewrite this, make it a little bit easier to solve. So I'm going to rewrite that 1 divided by square root of x minus x is equal to, ooh, I messed up. Hopefully you caught it. I did make a mistake. Look for my mistake, and then I'll correct it. So I made a mistake here. I was getting ahead of myself. When I took the derivative of 2x to the half, that's x to the negative half. But the derivative of negative x, actually this should have been minus 1. So that should have been minus 1, and that should have been minus 1, minus 1, and minus 1. Okay, so now how can we solve this? Anytime we have a radical, now you could add 1 over and cross multiply, that works. But anytime, I have a fraction. Whenever I have a fraction, the way I like to get rid of a fraction is to just multiply every term by the denominator. So anywhere where we see a plus or a minus, we're going to multiply by the denominator. So that cancels out. I get 1 minus square root of x equals 0. Add square root of x to both sides. 1 equals the square root of x. Can the square root of an answer be positive? Yes. Right, that works. So now we're going to square both sides. So square the right side and the left side. And the reason we do that is that cancels out our radical. So we get 1 equal to x. And so that we're verifying, right? They asked us to verify our answer. Right, where did it have a horizontal tangent line? At 1, we got it right. So we proved it algebraically. Okay, now this is a little bit of review from Monday. On what intervals is g prime of x less than 0? So what does g prime of x less than 0 represent, right? We took notes a few days ago. We had that table, that chart. G prime of x less than 0. Whenever you see that, you want to connect that to g of x is decreasing. Okay, I'm going to say it one more time. G prime of x less than 0 is g of x is decreasing. How am I going to know where this is decreasing? Well, we know that it's going to change at 1, right? Because that's where we have that horizontal tangent. So on the left side, it looks like it's increasing. On the right side, it looks like it's decreasing. So we're going to say basically g prime of x is less than 0 for 1 to infinity y, because g of x is decreasing at that interval, or you could say at 1 to infinity, or for 1 to infinity if you don't want to use at. I like to use at for a point, and I like to use for intervals. It helps me to kind of separate the two. I know one of you guys, I think it might have been Anthony, one of you guys was asking about that being a little bit confusing for you. So if you want to, you can always use the word for whenever you have an interval, like from 1 to infinity. You use at if you just have one specific point, like at x equals 1, that's just 1 point. So that might help out. Where is g prime of x greater than 0? Right, we want to connect g prime of x being greater than 0. We want to connect that to when g of x is increasing. So where is this graph increasing? It's increasing on the left side. Now it starts off at 0, right? So g prime of x is greater than 0 for 0 to 1. If you put a bracket at 0, you would actually be okay here. I'm going to leave it without, but either way would work. Some textbooks will do brackets, some won't. I like to, anytime I'm doing increasing, decreasing, I just use parentheses. It makes it easy. You're going to get full credit no matter what. So for that interval, or for 0 to 1. Okay, next says, For what value of x is the slope of the tangent line equal to 2? As soon as I see the word slope, especially slope of the tangent, as soon as I see this word, I want to immediately jump to derivative. I want to immediately think derivative. So what this is saying is, when is the slope equal to 2? We already got an equation for the slope. That equation for the slope was 1 over square root of x minus 1. So we're just going to equal that to 2. Okay, add 1 to both sides. 1 over square root of x equals 3. And you could either cross multiply or multiply by the square root of x. Actually, I'm going to even do it that way. So just to kind of show and be consistent with how I did it. It's probably easier to add 1 first, but just to be consistent, I'm going to do times square root of x times square root of x times square root of x. So this gives us those cancel. We get 1 minus square root of x equals 2 square root of x. Okay, then up here, add square root of x to both sides. We get 1 equals 3 square root of x. If you're worried about the square root of x, don't worry about it. If I had 1 minus x equals 2x, it's really easy. Just add x, you get 1 equals 3x. This was the same thing, but with a square root. Okay, divide by 3, 1/3 equals square root of x. How do I cancel out a square root of x? We do the opposite of it. The opposite of square rooting something is squaring it. Put a parenthesis around both sides and square it. 1/3 squared gives us 1/9. So where does x have a slope of the tangent? The slope of the tangent line being 2, whereas the g prime of x equal to 2 is at 1/9. Okay. And the last one says, find an equation of the tangent line at x equals 4. So whenever we see the word equation of a tangent line, we always do x1, y1, and m. Now x1 is 4. To get y1, you're going to plug in 4 to the equation. So 2 square root of 4 is 2 times 2 is 4. Minus 4 is 0. Plus 2 is 2. You get 2. Or, if you're smart about it, just look on the graph at that point. The coordinates of that point are 4, 2. Okay, so we could have just said, oh yeah, it's 2, based on the y value. So, but this is always plugging into the original equation. So in this case, the original was g of x. Right, and then m is always plugging into the slope into g prime of x, into the derivative. So that's just making sure we're clear on that. So we know that g prime of x, we've done this equation, right? We already solved for it. We don't have to redo it. G prime of x was 1 over square root of x minus 1. So that means that g prime of 4 would be 1 over square root of 4 minus 1, which is 1 over 2 minus 1. A half minus 1 is negative 1/2. 1 over 2 minus 2 over 2. Right? And we don't do plus or minus 2 here because it was a function, right? When we're solving for x, we'll do the plus or minus. But when we're plugging into a function, we only do the positive side. So this gives us y minus 2 equals negative 1/2 times x minus 4. Okay, and then it says, then draw the tangent line on the grid. So if we were going to draw that tangent line, we know that the point is at 4, 2. So the point is at 4, 2, and the slope was down 1 over 2, down 1 over 2, up 1, left 2, up 1, left 2. And you could take a ruler and connect those into a line. Okay. I'm going to do my best on the tablet, but it might not be perfect. But that would be our sketch of our tangent line. And you would see really, really close to 4, those graphs really overlap. But then as we get further and further away, they're not going to overlap as well. Okay. All right, next question. The table of values. So instead of giving us an equation, now we have a table. Okay, everything's going to work very, very similarly, but we just have a table. So the table of values below shows the derivative of h prime of x. The zeros indicated in the table are the only zeros. This is very, very important. Okay, if it doesn't tell you this, then we actually can't answer this question at all. Everything would be we don't know. And the reason for that is if there could have been other zeros, see how like basically we have -8, -5. So we don't know what -7 was. We don't know what even -6.5 was or -6.4 was. right? We don't know what -6 was. We don't know what -5 was. So we only know that, we have an 11 here and we have a 5 here. So do we actually know that it was always a positive value here, right? Do we actually know that it was always positive? Well, if it didn't tell us that those are the only zeros, we don't, right? Hypothetically speaking, it could have gone to 0 and then gone to like, oops, it could have gone to a negative value like -4. And then it could have gone to, 0 again, and then it could have gone up to, say, 2. And if that would have happened, what would happen is our graph would change between increasing, decreasing, increasing, decreasing at these other spots. But we don't need to worry about any of that because it tells us that these zeros are only zeros. That's pretty important. We'll get to that more, especially next semester when we talk about some of this stuff. But for right now, just kind of trust me that when we say that, it's important. So on what intervals is h of x increasing and when is h of x decreasing? So again, we want to kind of think back to the table from Monday, right? What does h of x increasing match up with? That would match up with h prime of x being a positive number, being greater than 0. And what would h of x decreasing match up with? H of x decreasing would match up with h prime of x, its derivative, being less than 0, being a negative value. So because these are my only zeros, right? That's a 0 and that's a 0. I know that anything smaller than -2, right? Anything smaller than -2, anything going this way is going to be the same as these numbers, is going to be positive. Anything in between -2 and 7, those are all negative values. And anything after 7 is going to be negative again. So that's kind of showing us. And yesterday we did the whole number line analysis. Okay, if the table is weird to you, I actually always do these with a number line analysis because it makes it so much easier. So I'm going to show you, this is the way I like to do it, and it's really, really easy. Is just do that same number line that we made yesterday. We're going to label it as h prime. And we're going to put in our zeros. Our zeros are at -2 and at 7. So at -2, I'm going to put a 0. And at 7, I'm going to put a 0. And then we're going to just plug in a test point. Any test point to the left of -2. To pick -5, I could pick 8. Either way, I get positive. Then any test point in between 0 and 7. I could pick any one of these, 0, 3, or 5. And any one I plug in, I get a negative value. Then 7, I could either pick 10 or 12. It doesn't matter. I get another negative value. So I really like to do this. It really helps me. I even do this on graphs sometimes, right? It just helps me to really stay clear. So I'm increasing, decreasing, and decreasing. So on what intervals is h of x increasing? We'll say h of x is increasing for -infinity to -2 because h prime of x is greater than 0. And I'm going to use 4. I'm going to try to be consistent with that because it's an interval for that interval. Okay, then where is h of x decreasing? H of x is decreasing. We're going to split those up for -2 to 7 union 7 to infinity. Why did I go out to infinity and not stop at the endpoints? Is because it says those are the only zeros, so we know we can just keep going, right? And it's a polynomial function, so it's going to be continuous for every single value. It didn't say that it stopped at -8 or 12. So why? Because h prime of x is less than 0 for those intervals. So you didn't have to make your number line analysis. I just chose to. If you could do this in your head without making your number line analysis, great. But it really helps me out, so I like to make it whenever I can. Okay, when would h of x have a maximum? Again, my number line analysis is really going to help me here. You just see, oh, there's a maximum right there. So it has a maximum at h of x, kind of sentence starter, has a max or a relative max at x equals 2, -2. I'm using at because it's a point. Because h prime of x, always the same reasoning, always because h prime of x changes, right? Just use your chart, your table that we're memorizing. Changes from positive to negative at x equals -2, or at that point. Okay, relative minimum. If we look on our number line analysis, there's nowhere where it points down, where it goes from negative to positive. So we're going to say, basically no relative minimum, or you could say h of x doesn't have a relative minimum, because h prime of x, we still need to justify it. Even though it's none, we still need to justify it, because h prime of x never changes from negative to positive, right? Negative to positive is for minimums, positive to negative is for maximums. Okay, if h of 3 equals 2, what is the equation of our tangent line at x equals 3? So if we ever see equation of tangent line, we always do x1, we do y1, and we do m. So x1 is 3, y1 is 2, right? x1, y1. Okay, and then for m is our slope, right? So y1 is always the original, right? It's always h of x, right? h of 3. And m prime is always our slope. It would be h prime of 3. So that's going to actually be on the table here. H prime of 3 is -3. So it's from that table, from the chart. So now we can say y minus 2 equals -3 times x minus 3. Now, make sure that you always read the full question. First, it says, what is the equation of the tangent line? And there's a question mark, but then there's more. So read that. What is the equation of the normal line? So I'm going to label these. That's our tangent line. And for our normal line, we just use the opposite reciprocal slope, but everything stays the same. Y minus 2 equals positive 1/3 times x minus 3. You could rewrite x1, y1 and put like m perpendicular, but it's always the same x and y, so I just flipped the slope. Okay, now this next one is new. Find the tangent line approximation of h of 3.1. We haven't done this yet, but we kind of led into it in the first example. Okay, remember back in that first example, we did the plug-in for -3.9, and we saw that they were really close, and so we said we could approximate. So whenever you see a tangent line approximation, it's always going to be the same thing. So whenever we see tangent line approximation, our first step is always going to be to write the tangent line. And then our second step is, what I do is I plug in the x, and then what I like to do is I change the y to be like, basically f of whatever we're approximating, or in this case it would be h. So since we're approximating for h of 3.1, we're going to change the y to h of 3.1. So we already have the tangent line. We already did step 1 here. Okay, I'm going to use another color. So we already did, this one, and we got y minus 2 equals -3 times x minus 3. Okay. And so now what we're going to do is we're going to change the y to h of 3.1. It's just like having a y. Minus 2 equals -3 times, and instead of equals, actually another really, if you want to get some bonus cred from your grader, you change that to an approximately. So it's approximately equal to 3.1 minus 3, right? Instead of x, I wrote 3.1. Some textbooks will leave this as a y until the very end, right? They'll just keep it as y because it's easier to solve. And then at the very end, they'll change it to h of 3.1. That's okay. If you want to do that, that's okay. I like to change it now, otherwise I forget to. So just know that h of 3.1, it's just like having a y, we're just isolating for that. So h of 3.1 minus 2 is approximately equal to -3 times 3.1 minus 3 is 0.1. Okay, I showed you guys this in that other example. We should be really confident multiplying. 3 times 1 is -3 times 1 is -3. Move the decimal over once, -0.3. Oops, and don't do what I did. I totally forgot to write my minus 2. So h of 3.1 minus 2 is approximately -0.3. Then we're going to add the 2 over. and we get h of 3.1 is approximately, when I add 2, be careful, negative 0.3 plus 2, that's like 2 minus 0.3. 2 minus 0.3 is 1.7. Okay, be careful about those. It's not 2.3, right, because it was negative 0.3 plus 2, that's 2 minus 0.3. If you need to, 2.0 minus 0.3, borrow 1, 10, 7, 1.7. Okay, and then find the value of each of these limits. This is going to go back to first chapter. We're going to build on every single chapter is going to connect to the previous chapters. We can't just forget about it. So in this case, okay, finding the limits, we don't have, a top is bigger, a bottom is bigger. We just have our table. So normally when we're doing the limits out to negative infinity and positive infinity, we were looking at like, was the top bigger than the bottom? That went to infinity or negative infinity. Were they equal? Then it was a over b. And was the bottom bigger? It was 0. But we can't do that here because we don't have an equation. But what we do know is that this graph never goes back to 0, right? It never ever goes back to 0. So what do we know, kind of, if we think about going to, in this case, is negative infinity? What do we know about going out to negative infinity? We're going to the left. And what's happening here is it's basically at negative infinity. These numbers now, we want to be careful, is we know that kind of our graph was increasing. So this is tough, okay? Our graph was increasing. Okay, it was getting bigger and it was getting bigger and it was getting bigger and it was getting bigger. So if we think all the way to the left on an increasing graph, what is this graph doing? It's going down, right? This graph is going down. So our limit as x approaches negative infinity will be equal to negative infinity. And that's, if we wanted to justify it, we knew that the graph was increasing, right? So if we kind of, this is kind of the graph is increasing, then it decreases more. So if a graph was increasing, well then on the left side, it's going down. As we go to the left, it's going down. And then next, for positive infinity on the other side, right, positive infinity would be our far side. And on that far side, it's not increasing, it's decreasing, but it's also going down, right? Because we read left to right. Here we had to, on the other one, we had to read backwards because we're going to the left. So this one is also going down, right? Because it's decreasing there. So it's going to go to negative infinity. So that was a really tough concept. This is definitely kind of a challenge question, but it's something that I really do want us to try to understand and kind of realize how we did that, is we looked at that increasing and decreasing concept. Okay. We're going to do the same thing, but now we're going to do it for a function, and we're going to think about our tangent lines again. So this video is getting a little bit longer. We're going to try to finish up in the next 10 minutes. We're going to go through fast, okay? So this one, on what intervals is f prime of x increasing? Remember I told you guys in yesterday's video, whenever we see increasing, decreasing, or we see maximum, minimum, or we see critical point, our first step was always to take our derivative. In this case, they gave us the derivative, x times x, 2 minus x times x plus 3. We're going to take our derivative and we're going to set it equal to 0. Now, we don't have to take the derivative, it's already there. So this part, x could be 0, or this part, 2 minus x, could be 0, or this part, x plus 3, could be 0. Okay, sometimes I'll kind of put a little kind of tab there. So this is x equals 0. This one's going to be x equals 2. And this one's going to be x equals negative 3. So I'm going to put my number line up here. Just give myself a little more room. F prime. I have negative 3. I have 0. And I have 2. And we're going to plug in numbers in between those. So I'm going to plug in, say, negative 4. If I plug in negative 4, I get negative 2 minus negative 4. 2 minus negative 4 is like 2 plus 4. That's a positive. And then negative 4 plus 3 is a negative. A negative times a positive times a negative is positive. Okay? Then let's plug in negative 1. Negative 1 is negative. 2 minus negative 1. That's going to be 2 minus negative 1. 2 plus 1 is positive again. So actually I can leave that positive. And negative 1 plus 3, this one turns positive. So negative times positive is negative. We're just checking signs. We're not actually checking the values. We're just plugging in signs. Okay? 0 plus 1. 0 plus 1 is positive. 2 minus 1 is positive. And 1 plus 3 is positive. And then finally say like 3. Okay? 3 is positive. Now 2 minus 3, that's a negative. And then 3 plus 3 is positive. Positive times positive is negative. Okay, super cool shortcut is the only times these ever repeat are when you have like an x squared or an x to the 4th or an x to the 6th, an even one. So if you don't have any squareds here, then it can never repeat. So you know that whatever you get for the first one, so I got positive, it's always going to switch positive, negative, positive, negative. So that's kind of a really cool shortcut, is the only time they ever repeat are when we have an even exponent. Anyways, if I drew this, right, it's increasing, then it's decreasing, then it's increasing, then it's decreasing. So it said, where is f of x increasing? F of x increases for negative infinity to negative 3, union 0 to 2. Why? Because f prime of x is greater than 0 at these intervals. Right? This is review from yesterday. But just a little bit of a different take on it, because now we started off with the derivative already. We didn't have to actually solve for it. Then f of x decreases for negative 3 to 0, union 2 to infinity. Same reasoning, but just flipped, because f prime of x is less than 0 for these intervals. And I said I'm going to try to use the word for if I can with intervals, so we'll do that. Okay, when does f of x have a relative minimum? Okay, there's one spot and it's at 0. Right, 0 is where we have that minimum. So where does f of x have a relative minimum? Okay, so you could say f of x has a relative minimum at x equals 0 because f prime of x changes from negative to positive. Okay, you probably want to write the sentence starter, but we're running out of time, so I'm going to just try to go as fast as I can. But saying f of x has a relative minimum would be nice. When would f have a relative maximum? Same thing, start off, f of x has a relative maximum at, x equals 2. Oh, and up here, because f prime of x changes from negative to positive, we always need the at x equals 0. Don't forget that. So f of x has a relative maximum at x equals 2 on 18 because f prime of x changes from negative to positive. And actually, there are two answers. You should have two answers. This is my fault. I messed up. 2 is an answer, but also negative 3. So x equals negative 2 and x equals negative 3 because f prime of x changes from positive to negative at these points. See, now I'm going too fast and I'm wasting our time. Positive to negative at these points. Okay, and then finally, they give us an f of 4 equals negative 1, and they want the equation of a tangent line. As soon as I see equation of a tangent line, x1 is 4. y1, that's going to be the plugged into f, right? That's going to be plugged into f, so that's negative 1. And for m, this is plugged into f prime. So we're going to do f prime of 4 for our m, right? And we have an equation, right? We already have this equation. X times 2 minus x times x plus 3. So x times 2 minus x times x plus 3. That's 4 times negative 2 is negative 8 times 7 is negative 56. So a very, very large magnitude for a slope, but that's okay. So what's our equation? Y minus negative 1 is going to become y plus 1 equals negative 56 times x minus 4. Okay, and then I probably, in this case, I can't even plug in 4.1. I literally cannot plug in 4.1 because I don't have an equation, right? We never had f of x. We don't know what f of x is. So if I asked you to plug in 4.1, you couldn't. But you can approximate it using the tangent line. So that's another reason why we need to be able to approximate using the tangent line. So now we said that we replace y with f of 4.1. We're going to replace our equal signs with an approximately sign. And then we're going to replace our x with 4.1. So we get f of 4.1 plus 1 is approximately to negative 56 times, I'm going to kind of skip a step, 4.1 minus 4 is 0.1. Negative 56 times 0.1 is going to be negative 5.6. And subtract 1 to both sides, f of 4.1 is approximately to negative 6.6. Then it says explain why this is a good approximation for the true value. And so the reason it's a good approximation is basically it's a good approximation because 4.1 is close to x equals 4. So the tangent line will approximate or will be close to the function. If we want to, we could say at x equals 4.1. Okay, you're never going to ask to explain that, but it's just for us. Okay, on what interval, last one, questions 21 to 25. So this is kind of wrapping everything up. I know this is getting really close to an hour-long video, but this is just a kind of a really hefty subject, and I really want to go over these different ways that we could see it with a graph, with the derivative, with a function, and then this one is with the graph of the derivative. So we want to be careful on this one. This is not the graph of the original, but this is the graph of p prime of the derivative. So really thinking about what does that derivative mean, going back to that table from Monday, that chart. The derivative equals 0 means we have a horizontal tangent line. The derivative is positive, greater than 0 means that we're increasing. So on what interval is the graph of p of x decreasing? So what are we going to think? P of x decreases when, with that chart, when p prime of x is less than 0. That's what we want to kind of remember. So where is our graph less than 0 here? Our graph is less than 0 from negative 3 to 0. And from 0 to 3. And what I like to even do is, before I do anything, a lot of times I like to just draw in my zeros, right? My critical points. So I have critical points at negative 3, 0, and 3. That's going to help me out. So we're going to say p of x is decreasing or decreases for negative 3 to 0, union 0 to 3, because p prime of x is less than 0 for those intervals. Okay, and then increasing is just going to be our opposites. Increasing, p of x increases where it's positive, so for negative infinity to negative 3, union 3 to infinity, because p prime of x was positive there, was greater than 0 for those intervals. If you don't want to write less than 0, you could write is negative. P prime of x was negative. If you don't want to write greater than 0, you could write p prime of x was greater than 0. But please, 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 like I said, never, ever, ever, ever use it. You never want to say because it is positive. You want to say because p prime of x is positive. Okay? When would p of x have a relative maximum? So remember, relative maximum would be when our derivative changes from positive to negative. Again, not when it changes, when p prime changes from positive to negative. So that's at negative 3, it goes from positive to negative. So p of x has a relative max at x equals negative 3 because p prime of x, do not say it, because p prime of x changes from positive to negative. And then again, we need the at x equals negative 3. Okay, minimum, now we want it to change from negative to positive. That's going to be at positive 3. It goes from negative up to positive. 0, see how it stayed? It was negative and then it's negative again. So 0 is neither one. Okay, so p of x has a relative minimum at x equals 3 because p prime of x changes from negative to positive at x equals 3. I want to talk about 0 really quickly. 0 is a critical point. So if it asks for critical points, 0 is a critical point. But 0 is not a maximum or minimum because it didn't change, because the derivative did not change signs at 0. Okay? Approximate the value of p prime of 1.8 using a tangent line approximation. So as soon as we see tangent line approximation, we know first we need to write the equation. So x1 is 2. y1 we're going to use as negative 3 because that's the original, that's p. And m, we need to get the slope. We need to know what p prime of 2 is. Well, p prime of 2, we have a graph of p. So p prime of 2, the value here is, the point is 2, negative 4, right? That's why we practiced identifying that. So p prime of 2 is negative 4. It's from the graph. So now we have y minus negative 3, y plus 3 equals negative 4 times x minus 2. So that was our first step. Now we want to approximate p of 1.8. So we're going to change y to p of 1.8 plus 3. We're going to change the equals to be approximately. And we're going to change x to be 1.8 minus 2. That's going to give us p of 1.8 plus 3 is approximately negative 4 times negative 0.2. Okay, 0.2 times negative 4. What's 4 times 2? 8. Or negative 4 times negative 2 is positive 8. But instead of positive 8, we need to make it 0.8 because it was one decimal place. So p of 1.8 plus 3 is approximately 2.8. Subtract 3 from both sides. Okay, negative 0.8 minus 3. Okay, when you do this, what I like to do is just, what would be 3 minus 0.8 would be 2.2, but because it's 0.8 first, it's negative 2.2. Okay, you can do it by hand or you can do it in your head. So again, what I did is, basically 0.8 minus 3. Well, 3 minus 0.8 is easy, it's 0.2, but since the negative 3 is bigger, it's negative 2.2. Okay, so we are going to work on the day 16 homework in class tomorrow. Email me if you have any questions before then, and I will see you in class.